We need to resume the last talk before the coffee break. Is going to be a Zoom talk. Kevin Morand is going to talk about graph complexes and the formation quantization of Lie bialgebroids.
Okay, thank you very much. So first of all, I would like to deeply thank the organizers for this very nice conference. So it's a pleasure for me to attend and to get the opportunity to discuss these results that has been obtained within the context of deformation quantization, in particular for Lie bialgebroids. So before going into the detail of this result, let me just provide some broad context. So by deformation quantization, we mean some research program which aims at providing some rigorous framework for quantization. So the main idea of this program is the introduction of a formal deformation parameter that we denote H bar, and which allows to distinguish between different layers of structures. So the paradigmatic examples of deformation quantization problem is for Poisson manifold. So in this case, we can distinguish between the classical, semi-classical, and quantum level. So the classical level in this case is just algebra functions on the manifold, which is an associative commutative algebra function that we will deform into a non-commutative associative algebra, what we call star product. And the semi-classical data, so the first order deformation in the formal parameter H bar, reproduces a Poisson structure. So the deformation quantization problem is, can we associate to each Poisson structure a star product which quantizes it? So the same can be done for Lie bialgebroids. In this context, the quantum object is a formal deformation of the symmetric algebra associated to a vector space. Deformation as a bialgebra, such that the first order deformation reproduces a Lie bialgebra. So the most important result within deformation quantization, at least for Poisson manifolds, is the Kontsevich formality theorem. So Kontsevich in 1997 introduced, proved his formality conjecture. He provided some equivalence between two differential Lie algebras that he denoted T-poly and D-poly. So T-poly stands for the Schratten-Lie algebra of polyvector fields on a manifold, whereas D-poly stands for much bigger algebra, the Orshi differential Lie algebra of multidifferential operators. So introduce some equivalence between the two. In particular, T-poly is a cohomology of D-poly. And this equivalence can be used in order to solve the quantization problem for Poisson manifold. Since this equivalence induces some bijection between the Mohr-Cartan sets associated to T-poly and D-poly. So T-poly controls Poisson structure or formal Poisson structure, and D-poly controls star products. So this equivalence allows to quantize any Poisson structure and to associate to it a star product. So another tool that has been introduced by Kontsevich and which will be relevant for us is so-called graph complexes. So these are families of cochain complexes which are made of graphs. So these are algebraic objects which are very easy to define. And these form complexes. So there's a differential that acts on these graphs. So for example, this is an example of a cocycle. And we've been interested in the cohomology of these graph complexes. So notoriously, this cohomology is very hard to compute. But there are some results available in the literature that we can use in order to gain some insights regarding deformation quantization problem. Okay, and the final piece of context is the so-called Grothendieck-Teichmüller group, or GRT1, which is an important and still vastly mysterious infinite dimensional group that has been introduced by Drinfeld, at least in this particular form. And this group appears in a wide variety of contexts in mathematics, and in particular, it appears in deformation quantization. So one of the objectives of this talk would be to introduce yet another incarnation of this particular group within the context of deformation quantization for Lie bialgebroids. Okay, so we introduce these four areas of these domains of mathematical knowledge. So now let's just make some connections between these four areas. So as I mentioned before, the formality theorem provides a solution to the deformation quantization problem for Poisson manifold. So from this formality theorem, we can deduce some star product formula, which quantizes any Poisson vector. So this is a Kontsevich star product formula, which is so an expansion in terms of H bar. So the zeroth order is a classical level, just a commutative associative product of function. The semi-classical level at order 1 is given by the Poisson bracket. And then we have this prescription in order to define higher orders at any order in H bar. And this is given by some expansion on admissible graphs. So these are admissible graphs defined by Quantization. And this formula can be checked to be associative, but non-commutative. So we retain the associativity, but we relax the commutativity of the classical product. This is universal, which means since it is written in terms of graphs, then it is valid for any Poisson vector. And it's also valid in any finite dimension. So indeed, when for infinite dimension, then the formula breaks down due to this kind of graphs, which contain some cycle, which is a directed path from one vertex to itself. And this cycle will introduce some traces, which are ill-defined in infinite dimension. So this formula breaks down for infinite dimension, but still it is valid for any finite dimension. Okay, and finally, there are some coefficients that appear in this formula, and these are given by some transcendental methods. So they are computed using some integrals over configuration spaces of points. Or more generally, these are given by an algebraic object called a Drinfeld associator, on which the quantitative mirror group acts. It acts on the space of this Drinfeld associator. Anyway, so this formula, in fact, can be interpreted as a Feynman diagram expansion for the BV quantization of the associated Poisson sigma model. So this sigma model has a source of dimension d equal 2. As we see for Lie bialgebra and Lie bialgebroid, we have the same kind of models, but in dimension 3. And this D will index different families of graphs. So this interpretation is due to Cataneo and Felder in 1990. Okay, second bridge we can make is between formality and graph complexes. So this has been also introduced by Kontsevich. It shows that this family of graphs, the graphs from the graph complexes, act on the admissible graphs of the quantization formula. And they simply act by insertion. So we can insert a graph from a graph complex into one of the vertices of the admissible graph. And then we can obtain a sum of graph by just summing over all the possibility to connect the dangling edges. So if we do this in the star product formula, generically, we will not preserve the associativity condition. In order to preserve it, we need, this graph should satisfy some condition. And indeed, it can be shown that whenever this graph belongs to the zero further cohomology of some particular graph complex, so here 2 is for d equal 2, corresponds to the source of the associated Poisson sigma model. So whenever the graph belongs to this particular cohomology, then one can show that the associativity of the star product is preserved. In fact, this comes from a deeper statement. We can check that more generally, the exponential group that we obtain by exponentiating this Lie algebra acts in a regular way on the space of universal formality morphisms, so on the space of Kontsevich maps. So the Kontsevich maps is not unique. In fact, there is an infinite dimensional space of Kontsevich maps, which is acted by this particular group. And in fact, this particular group is related to the quantitative mirror group. So in fact, this particular group is simply the expansion of some graded algebra, the quantitative mirror algebra, which is infinite dimensional. And it was shown by Wilfacher in 2010 that, in fact, the cohomology which is relevant, the graph complex cohomology which is relevant for us, is in fact isomorphic to this quantitative mirror algebra. So this is a very deep statement due to Wilfacher. So if we combine the different elements we saw, then we can conclude that this group, GRT1, acts regularly on the space of universal formality morphism. Or in other words, the formality maps form a GRT1 torsor, or principal homogeneous space. So we have this action of GRT1 on the space of formality maps. Okay, so this provides some incarnation. So first incarnation of GRT1 into the realm of deformation quantization. In fact, more generally, the cohomology of graph complexes will provide some information regarding some aspects of the deformation quantization problem. So one aspect of it is regarding the existence of universal formality maps. So universal meaning formality maps given by some expansion in terms of admissible graphs. So we can obtain some information regarding their existence by looking at the first degree cohomology of particular graph complexes. So for Poisson manifolds, it is a hard open conjecture that indeed this cohomology group vanishes, so that there is no obstruction. This is a conjecture due to Kontsevich and Drinfeld. Also, we can obtain some information regarding classification. So if some solution exists, then we can classify these solutions by looking at the zeroth order cohomology. And in this case, as I just said, the cohomology is just isomorphic to the contact mirror. Okay, so let me sum up the main idea of this talk. So once again, I would like to argue that deformation quantization problem can be characterized by the cohomology of suitable graph complexes. So the graph complex will differ according to which problem we are considering, but nevertheless, the idea is the same, that we can check the existence of universal solutions by looking at the first order cohomology. This is where the obstructions to quantization live. And we can also classify the space of solution by looking at the zeroth order cohomology. So this approach using graph complexity is not new. It has been already applied to different deformation quantization problems. So I mentioned about Poisson manifold in finite dimension, but also in infinite dimension. So as I mentioned, we need to remove the cycles from the formula. In fact, one can say that there is some obstruction to do so, as shown by these authors. So this obstruction, there exists some obstruction living in the first order cohomology of a particular group, particular graph complex. This is the so-called Kontsevich-Choquette obstruction, which prevents the existence of universal quantization formula for Poisson manifolds in infinite dimension. And also for Lie bialgebra, we can recast the solution to the quantization problem in terms of graph complexity. So the aim of this talk will be to add 2 threads to this ongoing story by discussing Lie bialgebroids, which are a common generalization of Poisson manifolds and Lie bialgebroids, and also some extension thereof known as quasi-Lie bialgebroids. So let me now present the results, and then I will give some argument how to obtain this result. So, okay, I said we can partition somehow into different categories the deformation quantization problems according to graph complex cohomology. So we have broadly 2 classes, yes-go classes in which everything works well, and a no-go classes in which there is some obstruction. So the yes-go class is characterized by conjecturally no obstruction to quantization, and also the grotatic mirror group plays some classifying role. So this is the case for Poisson manifold in arbitrary finite dimension. And also the Lie bialgebra and quasi-Lie bialgebra belong to the same category. So for all of this semi-cascade data, we can solve the quantization problem. On the other hand, we have a no-go class in which there exists some obstruction to quantization. And if this obstruction is hit, then there is no universal solution. Indeed, this is the case for Poisson manifold in infinite dimension. There is this Kontsevich-Choquette obstruction that lives in this first order cohomology, which prevents the existence of universal quantization formula for Poisson manifolds in infinite dimension. So the 2, new results I would like to propose concern Lie bialgebroids. So Lie bialgebroids, as I mentioned, are a common generalization of Poisson and Lie bialgebra, but surprisingly, Lie bialgebroids belong not to this yes-go class, but to the no-go class. So as I will argue for, there is some obstruction to the universal quantization for Lie bialgebroids. So this is kind of a no-go result. But on the other hand, if we extend the notion of Lie bialgebroid into quasi-Lie bialgebroid, then we recover the yes-go class. And in particular, we have some incarnation of the grotatic mirror group acting on quasi-Lie bialgebroid. So it doesn't act on Lie bialgebroid, but it does act on quasi-Lie bialgebroid. Okay, so now I will just precise a bit what I mean by this. So let me, for those of you who are not familiar with this notion, let me just precise what I mean by Lie bialgebroid. So as I mentioned, it's a natural candidate to unify both Poisson manifolds and Lie bialgebra. So very explicitly, a Lie bialgebroid is a vector bundle. So E over some manifold M. And this vector bundle will be endowed with 2 Lie algebraic structures. So we have one Lie algebraic structure living on E with anchor, row, and Lie bracket given like this. And we have also a dual Lie algebraic structure on E star with anchor R. And these 2 Lie algebraic structures are compatible in certain ways. They satisfy some quadratic compatibility condition. So, of course, one example of Lie bialgebroid is Lie bialgebra. So when M is just a point, then E becomes an ordinary vector space. And then the notion of Lie bialgebroid reproduces the notion of Lie bialgebra. So it contains Lie bialgebra, but it contains also Poisson manifold. So if we look at the tangent bundle and the cotangent bundle of the Poisson manifold, then both of them are endowed with a natural Lie algebraic structure, which are compatible. So Poisson manifold are also examples of Lie bialgebra. Okay, so this notion can be naturally recast within the graded geometry setup. So if we consider some particular graded symplectic manifold, which is endowed with a symplectic 2 form of degree 2, given explicitly in coordinates like this. So here we have 3 different coordinate degrees, 0, 1, and 2. So we have 4 different types of coordinates that we can use in order to build some canonical symplectic 2 form. We can associate to these 2 forms a graded Poisson bracket of degree -2. This is a so-called big bracket, a term that is used in the usual geometric approach to Lie bialgebra. And we can characterize Lie bialgebra as Hamiltonian function. So Hamiltonian function in this context is a function of degree 3, which satisfies some nilpotency condition, that is HH equals 0. So here we can construct some function using the structure constants associated to this data. So here we have structure constant from rho and f. So this is the Lie algebraic structure living on E. We have R and C, the algebraic structure on E star. And imposing this quadratic condition will reproduces all the consistency condition. For example, that this data from a Lie algebroid, this one as well, and also the compatibility condition. So this is a nice reformulation of the notion of Lie bialgebra due to Rothenberg. That in fact is crucial in order to define some graph action on this kind of structures. So in particular, we recover the notion of Lie bialgebra in this graded setup. If we get rid of all x dependence and the space-time coordinates, then we obtain the usual Hamiltonian function for Lie bialgebra. And also using the Poisson manifold, using the Poisson bivector, we can construct some anchor R and some C structure constant. Okay, but if you look at this formula, maybe you notice that there are some terms that are missing. For example, there are no terms which are odd order 3 in the coordinate xi. So this function should be of degree 3. So for example, xi, 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 or zeta, 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 or potential terms. But if we include this extra function, then we deform the notion of Lie bialgebra. So we're not in a Lie bialgebra anymore. We are in what we call either quasi Lie bialgebra or Lie quasi bialgebra. So for example, quasi Lie bialgebra are obtained by adding a function of this form, which is order 3 in the coordinate xi. So example of this quasi Lie bialgebra or quasi Lie bialgebra, which is a notion due to Drinfeld, and also the so-called twisted Poisson manifold, which are obtained by twisting the Jacobi identity for the Poisson bracket using some closed 3 form. Okay, so let me say a word about the deformation quantization problem for Lie bialgebra. So as we saw earlier for Poisson manifold and Lie bialgebra, we can introduce a similar quantization problem, but which unifies somehow the quantization problem for Poisson and Lie bialgebra. So this problem is due to Ping-Su in 1997. And the associated quantum object is a so-called quantum groupoid, which is a deformation of the symmetric algebra associated to a vector bundle as a bialgebroid, which is kind of a complicated object, which unifies the notion of star product and bialgebra. So Lie bialgebroid unify Poisson manifold and Lie bialgebra, and the quantum objects unify the bialgebra and star product. So this is natural candidate in order to formulate some quantization problem for Lie bialgebra. So we have here the classical data is a vector bundle, and then we will deform the symmetric algebra associated to this vector bundle as a bialgebroid, and one can show that the first order deformation indeed reproduces a Lie bialgebra. So this is a quantization problem, but contrarily to the Poisson manifold and Lie bialgebra, this is still open in full generality, so we don't have a full solution to this quantization problem. But we know that some particular cases are quantizable. So for example, Lie bialgebra and Poisson manifolds are both quantizable in this setup. So we can associate a quantum groupoid to Lie bialgebra and Lie bialgebroid associated to Poisson manifold. But in full generality, there is no known quantization formula for any Lie bialgebroid. Okay, but since, I mean, as I said, Lie bialgebra unifies the notion of Poisson and Lie bialgebra. So by analogy, we can conjecture that on the one hand, every Lie bialgebroid is quantizable as a quantum groupoid. So this conjecture was made by Xu in 1997. Since we know that every Lie bialgebra is quantizable and every Poisson manifold is quantizable, then why not be able to quantize any Lie bialgebroid? And second natural conjecture that we can make is that the space of quantization is acted upon by this Grotonic Teichmüller group, because this is the case for both Lie bialgebra and Poisson manifold. So these are somehow hard conjectures, and I mean, not much progress has been made since their formulation in 1997. And so the question I would like to ask now is, can graph complexes provide some insights regarding this quantization problem? In fact, as I would like to show, using graph complexes, we can provide some insight. And in fact, we provide some negative evidence for these two conjectures. So as we will see, it is in fact less likely now that every Lie bialgebroid is quantizable, because there is some obstruction to quantization. And also, it is less likely that the GRT1 group plays any role within the quantization of Lie bialgebroid. Okay, this is one of the last slides. So just to give some idea of what kind of graph we should use in order to act on Lie bialgebroid. So graphs come in many flavors, depending on what kind of problems we are regarding. So for Poisson manifolds in finite dimension, we need to use directed graphs. So just usual plane graph with just one color, which are indexed by, so each graph is characterized by two data, D, which is the dimension of the corresponding, the source of the corresponding Poisson sigma model, or sigma model. So D equals 2 for Poisson manifold and D equals 3 for Lie bialgebra, or Lie bialgebra. And also another ingredient is the number of colors which are oriented. So by oriented graphs, we need a graph with no cycles. So a cycle is a directed path from one vertex to itself. So if we remove all of these cycles, what we are left with is oriented graphs. And in order to act on Lie bialgebra, as shown by Merkulov and Pfeffer, we need to use oriented graphs. But doing this operation, like removing all the cycles, in fact, it changes the cohomology. So this was shown by Pfeffer and Zivkovic, that if we orient the cohomology of a graph with one oriented color is in fact equal to the cohomology of the graph without oriented colors, but in one dimension. So there is this relation between the cohomology. And this allows somehow to provide some novel incarnations of some familiar structures, but in higher dimension. So for example, GRT1 appears naturally in the context of Poisson manifold because it is the cohomology of this particular graph complex. But it also appears in one dimension higher if we orient one of the direction. So this is the reason why the Grotonic Teichmüller group appears both for Poisson manifold and Lie bialgebra. On the other hand, there is some obstruction, as we saw, to the quantization for Poisson manifold in infinite dimension. And this obstruction must have some counterpart in dimension 3. And in fact, this obstruction precisely occurs when we deal with Lie bialgebra. So, okay, so this is the last slide. In order to deal with Lie bialgebra, we need two colored graphs. So graphs with two different colors, red and so arrows that have two directions, red and black. And in order to preserve the space of Lie bialgebra, we need to orient both of the directions. So that means we are D equals 3 and C equals 2. That means we are just here. That means there is some obstruction. Whereas if we look at quasi-Lie bialgebra, so this more general notion of Lie bialgebra, then we just need to orient one of the direction. And if we orient only one of the direction, then we're here. And that means everything goes well and there's GRT1 and so on. So just by this simple observation of how many colors do we need to orient in order to act on Lie bialgebra and quasi-Lie bialgebra, we can obtain these two theorems. On the one hand, we have a no-go theorem saying that there is some obstruction to quantization for Lie bialgebra. This obstruction takes the form of some exotic infinity structure that deforms this big bracket for Lie bialgebroid. That means the quantization problem for Lie bialgebroid is very similar to the one for Poisson manifolds in infinite dimension, the one in which there is some obstruction. But on the other hand, if we look at quasi-Lie bialgebroid, then this is more akin to the usual one for Poisson manifolds in finite dimension. And then we know that there is some action of the Grothendieck-Muller group on quasi-Lie bialgebroid. So we have no-go result and also yes-go result. Okay, let me just sum up what I just said. I think time is going up. So yeah, we can partition the deformation quantization problem into different categories: a yes-go category and a no-go category. As I argued, rather surprisingly, Lie bialgebroid belong to this no-go category. That is, there is some potential obstruction to the quantization, and also the Grothendieck-Muller group plays no classifying role. So we can inverse somehow the conjecture made by Xu by saying that there are no universal quantization of Lie bialgebroids as quantum grouped. So this is, I mean, kind of negative result, but a more positive result is that if we look at quasi-Lie bialgebroid, then in this case, the quantization problem is similar to the usual one for Lie bialgebra. And that means there is no obstruction to quantization, conjecturally. And also we have some action of the Grothendieck-Muller group. So we can also, I mean, we can adapt the conjecture made by Xu by saying that given some differentiator, we can always quantize quasi-Lie bialgebroid, not as quantum groupoid, but as a more general notion of quasi-quantum groupoid, whose semi-Cascade data correspond to quasi-Lie bialgebroid. Okay, I think my time is up, so we thank you for your attention.
Thank you very much, Kevin. Any short question or comment here in the audience?
Hi, Kevin. It's Konstantin. Thank you for a very interesting talk. So, incidentally, I know there's this notion that generalizes both Lie quasi-bialgebras and quasi-Lie bialgebras called proto-Lie bialgebras, and it was also introduced by Kosman-Schwarzbach. So, yeah, do you have any ideas if there's a real result for those objects?
Right. So these are here, I think. So so indeed, there is notion of proto-Lie bialgebroid when you introduce both this I mean covariant form and this contrariant form. So in this case, there is some action, but this is yet another category. Maybe I can show you. Right. So this is here. So there is another category which I didn't mention, which is a bit peculiar, which is a bit middle way between the other one, in which we find the courant algebroids and also the proto-Lie bialgebroid, which are kind of courant algebroid in a particular, I mean, on the white Nissan, let's say. So in this case, there is no obstruction to quantization. This is not a conjecture. This is I mean, this cohomology is known, and there is just a one-dimensional space of quantization. But in this sense, this I mean, this class is a bit less interesting in the sense that there is no, I mean, no interesting cohomology. There is no appearance of GRT1, and also there is no, I mean, complicated exotic Lie infinity structure that we can obtain from this particular obstruction. So it seems that it is quantizable, but in a bit trivial way, in the sense that since the obstruction vanishes, here you can always, I mean, by induction, you can always construct step by step some quantization map, and the classification is also a bit trivial. There is only one loop, this triangle loop, which acts on the space of quantization. But maybe one more interesting aspect is that there is also some action of the degree -3, which corresponds to trivalent graphs, and which is an infinite dimensional space. So there is some action which is not shown here, but you can act on this space of quantization using these trivalent graphs. And this is a bit more interesting because it's infinite dimensional. It's a bit the avatar of the Grothendieck-Muller group, but in this odd dimensional setup. Yeah, thank you.
Okay.
Am I allowed one more question, or we have?
Yeah.
Okay.
Yeah, we don't have time now, sorry. But let's thank Kevin again for the nice talk.